Morning, Lamorinda Sunrise. Just a little look ahead. Next week, you're going to learn how to use AI to decipher whale language. Just to look ahead, just for you. But today, what we have is some people search the stars for answers. Our speaker formulates the answers himself. A Caltech professor of planetary science, he's reshaping our understanding of how solar systems form, evolve, and sometimes come to life. His groundbreaking research on exoplanets, planetary interiors, and the forces shaping our cosmic neighborhood has earned him global recognition, including a spot on Forbes 30 Under 30 as the next physics rock star. With over 100 scientific publications and stints at Harvard and Côte d'Azur Observatory, he's a leading mind in astrophysics. But when he's not deciphering the universe, he's rocking out, literally, as the guitarist and singer for his band, the seventh season. Today, let's turn up the volume on Discovery and give a stellar welcome to Konstantin Batygin.
I wanted to take a moment today to tell you all about a line of research that I've been involved in for really the last decade, and it has to do with the outer solar system. And I think it's timely and it's interesting because this year is really going to be a kind of a turning point from an observational point of view in our understanding of the outer solar system. I want to start this discussion by kind of dialing the clock back and recalling that, our census of planets, right, our census of planets in the solar system evolved very, very slowly over the course of the last few centuries, right? Everything out to Saturn, so like Mercury, Venus, Mars, Jupiter, Saturn, those planets you can see with your naked eye, so they were known already to the ancient civilizations. And the first planet that was discovered in a truly astronomical way was Uranus, and it was discovered by William Herschel, who just kind of looked at the night sky every night and noticed a slowly moving star. And that's actually the only planet that was ever discovered in a purely kind of astronomical way. The planet that followed, Neptune, was calculated. Its existence was inferred mathematically by Urbain Le Verrier in 1846. And since then, in 1930, what followed was the discovery of Pluto. And people didn't know that Pluto wasn't a planet when they discovered it. They mistook it for something much bigger, but Pluto is actually tiny. But it's actually maybe even more interesting, as Pluto was kind of a harbinger of more things to come. So what you're seeing here is the architecture of the solar system from top down. The pink circles are the orbits of Jupiter, Saturn, Uranus, and Neptune in expanding order. And that blue orbit, right, is the orbit of Pluto. So what we've learned over the last 30, 35 years is that really Pluto is an object which is a member of a much larger population of small bodies, minor kind of asteroids beyond the orbit of Neptune, that are collectively called the Kuiper Belt. Okay, and what you're seeing here is kind of a census. This is now about 10 years out of date. We know of more objects now, but this is a census of well-known, well-characterized orbits of small icy asteroids that live outside of the orbit of Neptune. Right, so a lot of people are familiar with, the belt of asteroids that is between Mars and Jupiter. It is creatively named the asteroid belt, but turns out the solar system has a second asteroid belt, if you will, well beyond the orbit of Neptune. And these guys are actually this belt is more massive than the asteroid belt, and it's quite remarkable, and it's mapping out the structure of this belt over the last 3 decades has revealed remarkable things about the solar system. Perhaps the first really revolutionary thing that the existence and structure of the Kuiper Belt revealed about the solar system is that the planets themselves, namely Jupiter, Saturn, Uranus, and Neptune, could not have formed where they are today. So in order to create this belt of icy debris beyond Neptune, in order to shape its orbital structure, the planets had to have migrated. And so the story of kind of early solar system evolution has been rewritten, where we now understand that the giant planets started out on orbits that were somewhat more compact, maybe a factor of 2 smaller, and the solar system was initially encircled by a annulus of rocky planetesimals weighing cumulatively about 20 Earth masses. And as the giant planets kind of scattered these planetesimals around, their orbits expanded and even for a moment went through a phase of transient chaotic dynamical instability, after which the orbits resettled to their current locations. And this, what you're seeing on the screen now, is not just like a movie that was made with AI or anything like that. This is output from one of our numerical models of early solar system evolution from about 2013 or so. So this is now kind of the accepted canon. I think everybody in the field agrees that indeed the planets went through a phase of instability, the orbits expanded, and so what we see now as the Kuiper belt, right, this population of icy debris, is actually the remainder of the original kind of disk of 20 Earth masses of icy planetesimals. And this model, this instability model of the early solar system evolution, has been wildly successful in explaining all kinds of stuff about the structure of the outer solar system, and it's been it sort of has worked itself into being widely believed. That said, one of the things that this model cannot explain, and this is something that that really got our attention almost a decade ago, is that if you go out and start to focus on the most distant orbits that we know of in the solar system. Now, for scale, right, this tiny ring now next to the sun, that's the orbit of Neptune. And these orbits that you're seeing now are the most distant bodies that we know of in the solar system. These are kind of icy asteroids that are about 100 kilometers across, right? So if you focus on that subpopulation, there is an interesting pattern that comes out that you can just see by eye. So first and foremost, the orbits of these distant, highly elliptical objects are all tilted with respect to the plane of the solar system by about 20 degrees. And also, they all kind of tend to point in the same direction, right? You can sort of see this by eye. To be clear, you guys are seeing this too, right? I'm not alone in, okay, it would be a problem if I was the only one, okay? The theory would be wrong. Okay, so this was something that we noticed back in really 2016. And over the years, this pattern has kind of evolved and strengthened as more data had been collected, right? So this is now the census of distant Kuiper belt objects from 2019. And this is what the census looks like, looked like in 2021. And it hasn't really changed since then. And so what you can see, again, just kind of by eye, is that there is a clustering of orbits, right? There's a confinement. There's some kind of a cosmic florist, which is putting together these orbits into a confined configuration. And moreover, this pattern correlates strongly with orbital stability. I won't maybe spend much time on this, but the fact that it correlates with orbital stability, in effect, tells you that this is not some artifact of, telescope strategy or anything like that. Okay, so this is what we see in the outer solar system. Why do we see this? Like, why are the orbits confined together? Generally, whenever you kind of query an astrophysicist, the first tendency, the first kind of impulse that every astronomer, astrophysicist will have will be to say, oh, the reason we see something in the universe or the structure of the solar system or whatever is because there was an event 4.5 billion years ago or 13 billion years ago or whatever, some distant time in the past, which shaped what we're seeing, and now we're seeing the relic. This is just kind of the Big Bang, inclination of the field. So could we explain what we're seeing in the outer solar system by invoking some event, say, during the solar system's formation, a star flew by, created this pattern, and now we're seeing this as a relic of of the formation phase of our cosmic home? And the answer in this case is absolutely not. Okay. And the reason the answer is absolutely not is if you take the solar system as it is right now and you let time go forward, right, then each one of these orbits will slowly rotate, slowly precess around. And this pattern of clustering that we're seeing right now would disappear in 100 million years. Okay? So a time scale that is short compared to the 4.5 billion year lifetime of the solar system. So something, if you really believe what you're seeing, like if you say, I trust the data, so to speak, then you need to invoke some kind of an object, some kind of a gravitational field that is external to Neptune, which is keeping these orbits confined. Okay? So we began a few years ago trying to understand exactly what kind of gravitational field, what are the properties of the objects that could be creating such a gravitational field, and have done thousands of numerical experiments, most of which look like this. So here, what you're seeing, again, the tiny kind of pink circle right at the center is the orbit of Neptune. For scale, that's 30 times it's about 30 times the distance away from the sun as is the Earth. The big pink oval that you see, that's the orbit of a new perturber, a body that we introduce in the solar system, which has not yet been observed. And the orbits that are dancing around chaotically are the orbits of the distant Kuiper belt. Okay, so for scale, the kind of gold greenish things are about their size is about 250 times the distance between the Earth and the sun, and the blue objects are bodies whose orbits are larger than 250 times the distance between the Earth and the sun. And if you let the clock, you allow the clock to kind of march forward, what you see is that in time, a pattern of clustering naturally emerges, right? We're about halfway right now in this simulation through the lifetime of the solar system. And right about now, I hope you're starting to see that the blue orbits are starting to get confined in a direction opposite of the major axis of the ellipse of this new body that we've introduced, right? You guys are also seeing this as well, right? The kind of surviving orbits are all pointing the opposite way from the direction into which the pink orbit of this new planet swings out. So
yes, we are seeing everything.
Okay, good. Yeah. So why is it doing that? Like, it took us a while to figure out why this clustering emerges. And the reason it emerges is when the orbits precess through orbital alignment with Planet 9, this new object. What happens is they go through they go through a maximum in their ellipticity. Okay? So they get maximally elongated. And when that happens, the periapse, so the closest approach to the sun of the ellipse, gets jammed into the orbit of Neptune, and then Neptune scatters them out. So the machinery in which this pattern gets carved out is ultimately has to do with an interplay between the gravitational field of this newly introduced planet, which is exterior to Neptune, and the scattering dynamics of Neptune itself. And we've done tens of thousands of these calculations, and what that has allowed us to do is to calculate the mass and the orbital parameters of the optimal body that can explain the data that we see in the outer solar system. And that mass turns out to be about 5 Earth masses. Okay? And the orbital period turns out to be about 10 to 20,000 years. We have kind of a factor of 2 uncertainty. So this means an orbit that's about 500 in semi-major axis is about 500 times the distance between the Earth and the Sun. And furthermore, the orbits must be mildly inclined with respect to the plane of the solar system, so about 20 degrees, and mildly elliptical as well. Okay, so that was really sort of the first line of evidence that we had for the existence of Planet Nine. This is back in 2016, 2017. But something that we noticed almost right away was that whenever we would run these calculations, right, every single run that was successful, right, every single run where we would match one aspect of the solar system, which is this clustering, would also produce objects like this insane ellipse that's coming out of the plane of the solar system. That's like a very robust outcome of every calculation that we've done. And so something that's inescapable, if Planet Nine is really there, is that it produces also a population of highly inclined, very much out of the plane bodies in the outer solar system that we do not yet see. Now, we do not, for the most part, we do not yet see them because most searches for objects in the outer solar system focus on looking in the plane of the solar system. So you're strongly biased to finding things that lie in the kind of orbital plane. And so we thought this would be a good prediction of our model, and effectively made the argument that if this putative planet that we're talking about is really there, then the solar system must be occupied by also high kind of things that are perpendicular to the plane of to the orbital plane of the existing planets. And then we went and looked through the data, and what we found is that such objects actually had been discovered. Right? They were sitting in some catalog, and this is what you're seeing now is sort of the census of these bodies, right? So you the kind of original clustering that I showed a few slides ago is now the set of orbits that are pointing up. The orbit of Planet Nine is shown here in orange or yellow, and this population of highly inclined objects are these cyan ellipses. And the reason they look so thin is not because they're so elliptical, it's because you are now looking at them basically top down. These are bodies that orbit in a perpendicular plane to the plane of the solar system. Now, no model of planet formation can generate objects that orbit in a manner perpendicular to the plane of the solar system. You need this extrinsic gravitational field to create them. And so this generation of highly inclined bodies really came in as a second important line of evidence that something is orbiting the solar system that we have not yet seen, and it's probably a planet. Okay, so I want to now kind of zoom back in and talk about a distinct discovery, which seemed to be unrelated at first, but turns out to be very much related. Some years later, after we had published all this, an object was discovered orbiting immediately outside of the orbit of Neptune on this nearly circular orbit, which you're seeing here. This was an object called Niku. And like, this was a distinct question. Okay, how do you create icy planetesimals immediately outside of Neptune's orbit that are perpendicular to the plane of the solar system? Initially, we didn't think that Planet Nine was anyhow involved because it's too close to Neptune for Planet Nine to have had an appreciable effect. But then we learned that this is actually yet another thing that naturally comes out of the solar system evolution calculations that I showed you a couple slides ago. So remember how if in the movie, which I showed, the simulation movie, right, we started out with a lot more orbits that we ended up with, right? Like we ended up with maybe 20, but when we started the simulation, there was 10,000. Where did they go? Well, a large fraction of them, as I discussed, got their perihelion jammed into Neptune and were scattered out. A distinct fraction was actually scattered in. And so returning back to that, to a simulation of that type, I'm going to focus on one particular body as an example. So again, for scale, we have the orbits of Uranus and Neptune as these pink ellipses. The orbit of planet 9 is this distant ellipse. And what you're seeing as a gold orbit is the dynamical evolution of one object in the Kuiper belt, which starts out far away. Now, under the gravitational influence of planet 9, it dances around, it does its chaotic kind of orbital dynamic. And when it hugs the orbit of Neptune, this particular object, instead of getting scattered out, gets scattered in. And its orbit eventually circularizes and kind of parks in a way which is quite reminiscent of that body that was discovered orbiting Neptune, on a perpendicular trajectory. And when we looked into this further, what we found out is that yet another line of evidence, another kind of dynamic that happens if planet 9 is there, is that there's a continuous kind of pollution of the outer solar system by retrograde objects that orbit the solar system in the wrong direction, if you will, and that such objects are really there. So here what you're seeing is a union of plots where you're seeing orbital inclination, so the tilt of the orbit on the y-axis, and kind of the size of the object of the orbit on the x-axis, and the blue dots there are real data points, right? So this population of distant kind of bodies that are retrograde is really there, and is another prediction that has come out of the calculations. Okay, so for a long time, the lines of evidence for the existence of planet 9 were really these four, right? It's the fact that if you go far enough away, the distant orbits are pointing into the same common direction. It's the fact that they are living in a common, slightly inclined plane. It's the fact that you naturally generate very long period of highly inclined bodies, and it's the fact that these retrograde objects that come in and get scattered in by Neptune. So those were the four lines of evidence for the longest time. In the last couple of years, we asked ourselves the question, is this it? Like, is there anything else? It would be disappointing to some extent if there was a whole new planet in the outer solar system and all it did were these four things, right? Like, are we missing anything? And we kind of looked around, shifted through our simulations, and then found that there is, in fact, one more thing. Okay. And that is that if planet 9 exists, right, then it should drive a steady flux of long period Neptune crossing objects. So let me expand upon what this means. So when we started out this discussion, right, we began our discussion with things that are confined together, that are all pointing in the same direction. And I talked about the longest period orbits, and I focused particularly on things that were dynamically stable, kind of mentioned that. And what we focused on in the last couple of years is actually the variant of that, the kind of flip side of that population of objects with long periods, but things that cross the orbit of Neptune, and therefore their evolution is unstable, meaning they're kind of on their way out of Neptune, is about to scatter them out to infinity, and they're gone. So if such a population exists right now, right, then it must be supplied by a continuous stream of objects being injected, because if not, they would all be gone already. And something that we noticed in the calculations that we've done is that indeed, if planet 9 is there, like in the plane of the solar system, it is continuously injecting long period objects that cross the orbit of Neptune. So for comparison, we've done two calculations. And these were rather computationally heavy, but what you're seeing now is a union of plots where you have the semi-major axis is the size of the orbit on the x-axis, the perihelion distance, the closest approach to the sun on the y-axis. In the case of a Planet 9 inclusive solar system on the left and the Planet 9 free solar system on the right. And the kind of 2D histogram just sort of tells you that if you have Planet 9 on the left-hand side, then what its existence allows you to do is generate a population of bodies with perihelion distance kind of between 15 and 30 astronomical units, like 15 to 30 times the distance between the Earth and the Sun. Whereas if it's not there, you don't have that population. So again, we went and looked through the data, and turns out the census of these Neptune crossers is now in kind of the tens of objects, and this is what the real data looks like. And I think, again, you can kind of look by eye and notice that there are lots of objects with a perihelion distance between 15 and 30. And the census requires the existence of Planet 9. And I won't talk about the process of debiasing, but the basic idea is that if you compare this existing data set to the simulation outcomes, you can rule out a Planet 9 free solar system at something like 5.5 sigma. So the probability, the other way to state it, is that the probability that Planet 9 is not there is something like 0.01%. Okay, so it's really, really, really low. Okay, the place that I'll perhaps end the discussion is with this slide. So for a long time, right, we've been data limited because it's really, really hard to discover these objects. Like, you go to the telescope, you have to stay up all night. The telescope breaks all the time. There's fog that rolls in. The upper atmosphere goes turbulent randomly, and it's kind of a slog. And so the reason we have kind of tens of these discoveries of these distant orbits is not because astronomers are lazy. It's because it's really, really tough to discover. But this new telescope, the Vera Rubin Observatory, which is fully NSF funded, is coming online this summer. Okay, so they're actually already getting engineering images now, but it's kind of starts full up astronomical operations in I want to say July, maybe August if there's a small delay. But this telescope that's going to be in Chile is going to it's kind of a next gen facility. Its entire job is to wake up every night and kind of look up and down the sky, left and right, and record everything it sees. And then the next night it does the same thing, and the next night after that it does the same thing. And then all it looks for are things that have changed on the night sky. So it's kind of the perfect observatory, both for discovering small distant objects as well as for looking for Planet 9 itself. So my hope is that as this new facility comes online, not only will our census of distant Kuiper Belt objects, the minor bodies, grow by an order of magnitude. My hope is that it will straight up just discover Planet 9 directly, and then we'll go back to living in a proper 9-planet solar system. Okay, so at this point, I'll maybe stop and take any questions. Thank you.
Thank you. That was interesting. So with all these objects out there spinning around, are there collisions that you know of or that you can predict? And then the follow-up question, are any of those objects headed here?
Yeah, great question. So when you ask the question of are there collisions, that question has to be qualified by collisions of what size. Okay, so the way that all populations of minor bodies work is all the mass is in a handful of large objects, and then there's a ton of tiny debris. So if you're talking about collisions among kind of millimeter grains, yes, there are. If you're talking about collisions of big, 100-kilometer objects, absolutely not. The Kuiper belt is effectively collisionless because space is big, and as you go far out, the just space between objects is so large that the probability of colliding two kind of 100-kilometer bodies is really negligible. Are any of the objects from the Kuiper belt headed here? They do perforate the inner solar system. In fact, there's a whole population of objects that are called Jupiter family comets. Okay, and Jupiter family comets are nothing more than Kuiper belt objects that have made their way into the inner solar system and been perturbed by Jupiter, scattered inwards, and then they turn on as comets. That's why we see comets, the short period comets in the first place. If not for the Kuiper belt, we would run out of them because comets evaporate. Should we be worried about Kuiper belt objects destroying the Earth? Absolutely not. We're much more, as far as things that strike the Earth, we're much more dominated by things that come from the asteroid belt, right? There's some, I forget the license plate of this body, but there's some dumb asteroid that has a 2% chance of hitting the Earth, a few years from now. This kind of a near Earth object. All of those things come from the asteroid belt, not the Kuiper belt. So Jupiter is a far more dangerous creature in the solar system, if you will, than Planet Nine.
So I recently read a book called How to Talk to a Science Denier. And in the book, I was told that 7% of the Brazilian population believes the Earth is flat. Can you give me an argument in a few sentences as to why my friends in Brazil are incorrect?
Well, I don't know. Have you seen a picture of the Earth from space? I don't know. It doesn't look flat. It looks like a circle. Yeah, this fascinates me because the number of people that believe the Earth is flat is going up, not down. That's an interesting fact for me.
I've got another question, if I might. What I've always found fascinating is that research is phenomenal. It takes time, energy, and money, but oftentimes the best outcomes are those that are offshoots from the original research and initiative. Are there other ways that your research is being used, other applications that have very little to do with the initial pure research?
So it's I think that perhaps the direction is the opposite. So we are using offshoots of other people's research, which I think are I would say that we are the parasites, not the not the other way around. Because, for example, we in the last decade, really, there's been this revolution in machine learning and AI, right? And what we have began to do is use some of the methods that have been developed for spotting cars by traffic cams and stuff like that to look for moving objects in the night sky. So we are kind of on the receiving end of those techniques. As far as our work and this being applied into a different direction, I'm sure that for it's being some of the methods for orbit propagation and stuff are being used, things like SpaceX, but nothing really to write home about that I would draw attention to.
My question has to do with these orbiting objects and sometimes their erratic behavior and their force. What influence do they have on our climate change?
Absolutely none. They have as far as the distant solar system, it doesn't contribute at all to our climate change. So if you're asking about the component of climate change, which is driven by orbital changes to the Earth, right? There is that component, but it goes the wrong way. So if you were to imagine we stop emitting CO2 altogether tomorrow, right? And we just like stop all civilization, then the orbital changes would take us into a part of we're in the part of the cycle where it's supposed to be getting colder, not warmer, because Pleistocene is over, and that has to do with the obliquity of the Earth. So yeah, it's really quite negligible compared to the anthropogenic component of climate change.
I have a question about the elliptical orbits. Why do they stay elliptical? Are they elliptical in the same ratios of length to width? They appear to be similar. And these sound like pretty small objects. And when they're getting extraordinary distances from the sun, I'm just incomprehensible that there's enough gravity to pull them back in again once they get that far away and they're that small.
Yeah. Okay. So the first question is, do they maintain the same ratio of the ellipse? They don't. Their eccentricities of the ellipse evolve, but when the ellipse, the way to think about it is when the ellipse is highly elliptical, right? When it's kind of in that kind of skinny phase, then then it's basically just more difficult to see by eye the changes in the ellipticity. But I assure you that it does evolve over long periods of time. And as far as you mentioned, the objects are small. They're small and they're difficult to detect. I mean, this is why this entire population has only been discovered really in the last 10, 15 years, right? Many of these objects are, 100 million times less bright than Neptune, right? So this is really on the cutting edge of what can be done right now with our telescopic capabilities. And as far as gravity, remember, all objects fall at the same rate under gravity, right? This is why these tiny 100-kilometer things can be used as tracers of the overall gravitational field of the outer solar system, if you will. There are lots of them, and they trace the dynamics much better than the planets themselves.
Buddy.
Okay, then I think Dan has one. Hey, did you hear the Flat Earth Society now has members all around the globe? Isn't that interesting? Well, my question is, how much do you rely upon amateur astronomers? How much does that come into play? I've read pieces about that.
Yeah. So unfortunately, with this project, very little. We were kind of hoping that we could marshal a lot more effort from it's not effort, it's marshal a lot more data from the amateur side of things, and that has contributed negligibly because these objects are so dim. It's kind of out of reach of what can be done by amateur astronomers. So there was a project out of, I want to say, Goddard, like NASA Goddard, to look for Planet 9 using amateur telescopes. They turns out they're orders of magnitude away from being able to make any detections that are interesting. But that same project did lead to the discovery of a bunch of brown dwarfs, which are kind of failed stars, if you will. And so that's an example where you start out looking for one thing, you don't find the thing you're looking for, but you find something else that's kind of interesting. So yeah, I think this is not in the realm of where amateur astronomers can make a dent, but that's my answer.
So we have Dan Herbert ask what wanted to ask a question.
Konstantin, thanks. Why pick Chile in the Southern Hemisphere? Is there a reason?
Why Southern Hemisphere? The reason is that part of the reason, if you will, is that it's great when you build telescopes in Chile. You just like the Chilean government will say, which mountain do you want? And then they'll just slice off the top of the mountain and say, here you go. All right. They're extremely easy to deal with. They are extremely kind of business friendly when it comes to, and like, so much of the Chilean economy is mining anyway, that the whole kind of supply chain and the ecosystem of building stuff on top of mountains is very well worked out. By contrast, ideally, where I would have loved to place this telescope is actually not in Chile, but on Mauna Kea, because Planet 9 is in the northern hemisphere, probably. So the one reason why this telescope might not be able to discover Planet 9 is that the Earth might get in the way because it's in the southern hemisphere, right? But Mauna Kea has been, a kind of a place where it's become progressively more and more difficult to put a telescope down, right? Because there's resistance from the local leadership, and there's no better example of this than the 30-meter telescope. I mean, the 30-meter telescope is a huge endeavor which has been stuck in limbo, might never get built on Mauna Kea because of the kind of now multi-decade long conflict which between kind of local tribal leadership and National Science Foundation, etc. So it's between nothing and the Southern Hemisphere, I will absolutely choose the Southern Hemisphere.
Thank you very much. We have time for one more question.
Thank you so much for a fascinating discussion. I'm curious if we know what these far Earth objects are made of. Do we have any idea?
Yeah, we kind of do. So you guys have heard of JWST? There's a new telescope that had launched, I think, a couple of years ago now. It was decades in the making. It was extremely expensive and got delayed a whole bunch of times. But anyway, it finally launched. It is now taking data. And one of the things that it can do is look at these Kuiper Belt objects and take spectra. And from this, you derive what the surface properties are. So being this far away in the solar system, you naturally expect there to be a lot of water ice. And that is something that we see a lot of. But we also see a lot of other interesting kind of organic products, right? And I'm not talking about like grocery store organic products. I'm talking about like things that are basically gunk that is created from irradiation of ice. So methanol, that kind of stuff. And it is now that whole field is injecting a big question mark into our understanding, because none of the populations of Kuiper Belt objects look quite like what we expected them to look like. Some of them look like the satellites of Uranus. Some of them look like, Trojan asteroids of Jupiter. Like it's a big confusion as to what all of this means. And it's exciting. We're just starting to work through that and starting to make sense out of all that. So yes, you can see what they're made out of, and we don't know what any of it means for now.
Thank you. Beautiful. Thank you very much.
All right. Thank you all. I really appreciated this.